What is going on, guys? In this video, I want to explain the paper behind the NeRFs, or neural radiance fields. And I want to introduce the concept of NeRFs. Basically, I want to explain how they work, what they do, and so on. And if this video is something that is interesting to people, and would be interesting to make a sort of from scratch implementation, then let me know and I can get working on that, depending on how popular that would be. So I want to explain it in a way that's easy, that doesn't take too long, hopefully. I don't know how long this video is going to be, but hopefully I'm aiming for 10 minutes. We'll see if I get there. It's probably going to be longer than 10 minutes, but yeah. All right, so let's just start with, what is the goal of NeRFs? And the idea is that we basically have some scene, in this case of drums, and we take a bunch of input images. Like we take a bunch of different images of this drum from different viewing angles, as you can see here. And the idea is that we can then train NeRF or run NeRF, optimize NeRF, and then we can synthesize a view of this drum kit. Or this scene in general. It's not a particular object, it's a scene. So basically make a 3D reconstruction from a multi-view image input. So from 2D images viewed from different angles, we can reconstruct a 3D scene and we can render new views. So here's an example they have from the paper, where basically have like a dozen of photos that are very like jumpy in the representation, but then when we use NeRFs, we get this very smooth sort of transition. And I don't know how smooth it looks like on the video, but in the paper, it's supposed to be very smooth. And I can also show you, I thought this, all right, so I also thought I could show you this. This is more recent research on NeRFs, which basically is instant NeRF, reduces the training time. But the idea is the same. So we have a bunch of input images, and then from that, it's able to make a complete 3D reconstruction from that, so we can see that we can move around completely in this new scene. So that's the cool part. NeRFs, that's what they do. Now let's get to basically, how do they work? And so this is the key part, and so I'll explain it. It's very simple actually when you actually get the idea of it. So you can imagine, for this 3D scene, if we're able to ask the model, what basically we have a point in this 3D environment. We say, we're interested in the coordinate x, y, z, if it's viewed from particular viewing angle of theta and phi. So, as a single pixel point in space, basically, we're interested in a single pixel point in space from a particular viewing angle. We run that through our network, F, which is just a fully connected neural network. Like it's super simple, super basic. And then the network outputs 4 values: RGB, the color of that particular pixel endpoint, and then the volume density, which is basically describing, is there actually something in space here? Like, is there actually an object here? And what is the density of that object? And so it basically describes also like the transparency of the material and so on. Hopefully that's an accurate explanation of what the volume density is, but it basically describes, is there something actually here? And so the network architecture in this case is just 9 layers of fully connected neural networks with each nodes, or each intermediate hidden nodes are 256, I believe. So it's super simple. And so you can imagine, if we can do this if we can do this for all the points in space from all viewing angles, then we can get a complete 3D representation of what that looks like. So that's the network architecture. Now I want to get to the key idea and the core concept of NeRFs, which might not be immediately, it might not be very obvious, but the idea is that the network will actually be specific to the scene. So we will overfit our neural network to the particular scene that we're interested in. And so I want to mark here that this is very unusual from how we usually do things in neural network training, because you could imagine, all right, so we train this NeRF, we send in all these different environments, and we train it on this multi-viewed input images, and then we can reconstruct the scene. And now all we do is that we just send in any arbitrary environment with this multi-view images, and then we get the scene representation. But that's not how NeRFs work. The neural network is actually specific. It's overfit to the particular scene that we're interested in. So basically, the network is garbage for other environments. It's only for the specific scene that we're interested in. So essentially, the network has condensed all the information from all the different viewing angles into a complete 3D representation in the parameters of the network. So this makes NeRFs very costly, because for each scene you have to train it, and then so basically, like, to do something with NeRFs, you have to train it completely. There's no like pre-trained NeRFs models around, because that's not how they work. So let's answer the big question, how does it all work? Because, all right, we just have this simple neural network, but you don't get the full picture. So step A. All right, step A. So we have these input images where we've taken them, right? And so what we do is that we send out this array of basically where we can sample coordinates in space. So we assume that this is from a 3D representation, and we send out an array from that, and then we know the particular viewing angle of the camera, right? So that theta and phi are known. And then we sample just random points along this particular line in space, and we say, all right, can you get the x, y, z coordinates of those points? And obviously, we don't know anything about those points, right? We don't know the color. We don't know if there is anything there. We don't know. But what we do know is that we can send this to our neural network. So we can send it in this intermediate step here. We get those 5 values. We send it to our network, and we get RGB and density output. Now, we know that these are going to be garbage, right? In the beginning, it's going to be complete rubbish. And the example or when we get to part B here, it actually looks like it does something that's, here it looks like it's been trained for a bit, because it can detect the color of where there's actually an object. But in the beginning, it won't, right? But so let's just say that we're looking at array 1. It outputs some guess of what the color and what the density is at each of these points. All right, so we get something from those points. And we have multiple rays, many rays, because each, you can imagine each input image sends out a ray, or a lot of rays, and then we have many points for each ray, and then we have many viewing angles for the particular scene. So what do we do next? So we have these guesses for the output of each point, for each ray, for each input image. So we take those, and now we basically use more traditional volume rendering methods. And in this case here, what we see is the density along each ray. So for ray 1, for example, in the beginning, there's nothing there. So the density is very low. This is just air. And then at some point we hit the particular object, and then the density goes up because it tells us, hey, there's something here. And then afterwards it goes down again, because now we've passed the object, or the scoop, or whatever. And so, you can imagine that depends on the ray that we send out from the viewing angle. But so basically what you can imagine is that, we do some way of computing all right, so let me explain this in a better way. So, the label that we have, right? The only label that we have is the point for the particular point in the input image. That's all we have, right? So we don't know the label for each of these points sent out from this ray. But what we can do is that we can sort of average them in a smart way using these traditional volume rendering methods. and we get, basically you can imagine, we take a mean of all the points, and then we say that the mean of these points for this ray should equal the point at this particular position in the input image. So the rendering loss in this case is we get some color output of how this looks like when we take the mean of the ray, and then we subtract, we take the L2 loss for the ground truth that we know. And now you might be asking, all right, so how does it actually learn what is what in these particular points of the ray? And the answer here is that since we have multiple viewing angles, the neural network can sort of figure it out and can know where where there's air or there's nothing and where there's an object. So let's just give an example. I don't know if you can actually see this, but let's just say that it from the second image, ray 2, let's just say that it takes a point where there's just empty space, and it shoots out a ray that hits one of these dots here that's white for the other ray. When we do this volume rendering for that particular point, they're all going to be space, right? So each point along that ray should be just white. And so in that way, it can learn that, all right, this particular point in space should be white because we know that from this particular viewing angle. And so we can sort of put that together. And then when we view it from another angle, which, we don't know necessarily that it's space there, we use the information from the other viewing angle, and the neural network can sort of figure it out that this is just space, and then it can do it in that way. Hopefully that gives some sort of intuition. Basically, the neural network figures it out. It's a magic thing. We just send it in and it works. Hopefully everything is relatively clear. Maybe this volume rendering is confusing, and so I'll explain and give some intuition around that. So the volume rendering, I probably am confusing you more now when I throw this up, but let's just give the intuition for this. So what we want to the left here, we want the color of a particular ray, right? So we're viewing a particular image, and we put a particular ray from that image. We want to get what is the color from the ray that we send out. So we take an integral, basically the way of taking a mean that I described simplistically, from some part beginning of the ray to some ending point of the ray. So the ray is one-dimensional, right? And the way that we sort of illustrate how far we're going in the ray is with the parameter t. So then we multiply three things here. And so the first one, capital T of t, which is how far we've gone along this ray, is basically describing how much light has been blocked up to this particular point t. So you might imagine, there might be like an object blocking in the beginning, and so then nothing will pass further on of the ray. So we want to know the information of that, and then we want to know what is the density at the point t that we're looking at. So we look at the ray for how far we've gone of the ray, which is at t now, and then from the ray we get x, y, z coordinates, and then we get the density at that particular point. And then lastly, we multiply with the color at point at r of t from a particular viewing angle d, and then this capital T of how much light has been blocked is an integral. Now I know that was fast. I know you probably know, all you need to know, okay, is that this volume rendering thing is basically from the 1980s, is a traditional volume rendering method. It's not specific to NeRF, but how it does it is that it multiplies, it takes a mean, basically, as I described simplistically, by looking at these three weighted, how much light has been blocked up to point T, the density at the particular point, and then the color at that point, and multiplies them and takes an integral. And that's the color. That's how we get the color for a particular array. So that's all you need to know. What we get with this traditional method is we get out a color for a ray that we've shot out from a particular point in this input image. All right, so now that we got this color, what we think is the color of the point from all the points of the ray, we need to compare it, right? So for the loss, we take a sort of L2 loss of the so this is a little bit confusing. I will get to this later on. We have two terms here, but just imagine we have this C hat, which is what we approximate or calculate to be the color of this ray that we've shot out, and what the actual color of the ray is. So we compare those two, and hopefully they should be the same, right? And that's the loss. And I will get to this C and F. It's a trick that they use. I will explain it in just a moment. So let's get to that's another trick. They use two tricks. I will get to that in a moment. But first, the first trick that they use, I showed you earlier that we have 5 parameters as input: X, Y, Z, sort of the point in space, and then we're interested in from a particular viewing angle. So it seems that neural networks don't work that well when we have, when this is maybe a little bit simplistic, but basically neural networks don't work well when we have very low dimensional features, because the weights are sort of basically neural networks work better if we have high dimensional data. So what they do is that they add these sine and cosines, Fourier features. They just take these X, Y, Z viewing angle. They do some transformation by doing sine and cosine of those values, and then they multiply by 2 and 4 and basically some power of 2. And they do that a lot of times until they get a higher dimensional space. So basically, then we will have that the neural network has more weights connected to the input, and then it seems to work better. But we're not adding any information. This is just a deterministic thing we're doing applying to the input to get higher dimensions. Yeah, that's pretty much it. So that's the first trick that they use. They actually made a separate paper to explain why this works. I haven't looked at it. But yeah. Anyways, so that's the first trick that they use. The second trick that they use is hierarchical sampling. So let's just look at this one to the left here. We have this camera. We send out this ray. We have some cloud, which is some object, right? We sample these rays, this point, this ray point, and then these are sort of at uniform distance, but we can then we get these points which are uniformly distant from each other. We run that through the network, and then we get the density, and we see that, all right, the neural network thinks that we hit something here. Maybe because the neural network believes it's hit something. Maybe it's more important to know the specifics of where there is an object. So what they do is that they then sample a second time, and they choose points close to the particular object that we perceive that we have found. So the idea here is that we can use more efficient sampling by not doing uniform, but rather that we have these coarse points, these uniform distance point from each other. We get something from the network where we get that there's an object, and then we sample a second time, where there's more importance because we know that there's an object there. We perceive that there's an object there. Sort of a second 2 times sampling method. And that is also, when we go back, I told you I would explain this, where we have color for the coarse point, C, and then the second term is the color for the finer points that we've sampled for the second time. So that's the loss function. All right, and that's it for this video. It got 20 minutes. All right, longer than I thought, but anyways, hopefully that gave you a good understanding of, first of all, why NeRFs, right? What they are, and then also how they work and the tricks that they use to make it work better. If you're interested in having a from scratch implementation, let me know if that would be interesting. And yeah, thanks for watching the video. Hope to see you in the next one.